Last commercial Morse code transmission in the United States was sent on July 12, 1999, at the Western Union offices in Middletown, New Jersey. The operator who sent it was a man named Walter Weimer, 67 years old, who had been sending Morse code professionally since 1952. The message itself was unremarkable, a brief formal announcement of the service's termination, transmitted to a receiving station in New Jersey and then printed on a teletype machine in the way that commercial telegrams had been processed for decades. The content was less important than the fact of its sending, the last pulse of a technology that had defined long-distance communication for 150 years, topped out by a man whose career had been built on its use and who understood, more than most people present, what was ending. Weimer had learned Morse code at 17, the same age that generations of telegraph operators before him had learned it, sitting beside an experienced operator, listening to the rhythmic patterns of dots and dashes, learning to hear language in electricity the way a musician learns to hear melody in noise. He had sent millions of messages in 47 years of professional telegraphy. He had sent birthday greetings and death notices and business contracts and love letters and stock prices and news dispatches. He had been, in the specific technical sense, the medium through which communication traveled, the human element in a system that converted language to electricity and electricity back into language. The last message took approximately 90 seconds to send. When it was done, Weimer set down the key, the simple mechanical device that made and broke the electrical circuit that carried the signal, and the room was quiet in a way that it had not been quiet before. The telegraph was over. The radio had won. But the story of why radio won and why it took so long, and what it cost, and what was lost, is not the simple story of better technology replacing worse technology that the history books tend to tell.
America, in 1899, communicated across distance in three ways. The slowest was the mail, physical paper carried by horse and rail and eventually automobile, delivering words to distant places in days or weeks. The fastest was the telegraph, electrical signals transmitted through copper wire at the speed of light, delivering words in minutes to any location served by the wire network that Western Union and its competitors had been building since Samuel Morse's first line between Washington and Baltimore in 1844. Between these extremes was nothing. There was no technology that delivered the speed of the telegraph without requiring the wire infrastructure that made the telegraph possible. The wire was both the telegraph's power and its fundamental limitation. A telegraph message could travel as fast as electricity to any point on the wire network. It could not travel at all to any point the wire did not reach. The wire did not reach everywhere. Ships at sea were beyond the wire. The open ocean, the route of every cargo vessel and passenger liner and naval warship that traveled between the continents, was a communication void. A ship that left New York for Southampton was, from the moment it passed beyond the coastal telegraph stations until the moment it came back within range of the European coastal stations, as isolated from communication as if the telegraph had never been invented. If a storm struck, if an engine failed, if a fire broke out, if a passenger had a medical emergency, the ship could not call for help and help could not reach the ship. The ocean was silent. Guglielmo Marconi understood what this silence meant. He was an Italian engineer with a gift for practical implementation, not a theoretical physicist, but a man who understood how to build things that worked. And he had been experimenting with wireless electrical signal transmission since 1894. By 1899, he had transmitted signals across the English Channel. By 1901, he had transmitted across the Atlantic Ocean. The first transatlantic wireless transmission was received on December 12, 1901, at Signal Hill in St. John's, Newfoundland. The signal, the letter S in Morse code, three dots, had been transmitted from a station in Paldu, Cornwall, approximately 3,400 kilometers away. The distance was further than any previous wireless transmission by an enormous margin. The technology was, by the standards of 1901 physics, barely comprehensible. Marconi had not invented radio in the sense of discovering the electromagnetic radiation that radio uses. That was James Clerk Maxwell's theoretical work in 1865 and Heinrich Hertz's experimental confirmation in 1887. He had invented practical wireless telegraphy, the ability to send Morse code without wires, using electromagnetic waves to carry the signal through the air and the ocean and the empty spaces between the wire network's endpoints. The significance of this achievement was immediately understood by every operator who had worked at a coastal telegraph station and watched ships sail beyond the range of the wire.
The ship that made wireless telegraphy a matter of public life and death rather than a technical curiosity was the RMS Titanic. On the night of April 14, 1912, at 11:40 p.m. ship time, Titanic struck an iceberg in the North Atlantic. At 12:15 a.m. on April 15th, its wireless operators, Jack Phillips and Harold Bride, began transmitting distress signals. The first signal was CQD, the standard distress call of the era. Minutes later, at the suggestion of Bride, they also began transmitting SOS, the new international distress signal that had been adopted in 1908 but had not yet fully displaced CQD in practice. The wireless calls were received by multiple ships. The RMS Carpathia, approximately 93 kilometers away, received Titanic's distress signals at 12:20 a.m. and immediately turned toward the stricken ship at maximum speed. The Carpathia arrived at the scene at approximately 4:10 a.m., after Titanic had sunk, but in time to rescue 710 survivors from the lifeboats. Without wireless, the Carpathia would not have known to come. The 710 survivors would have floated in lifeboats in the North Atlantic until they died of exposure. The 1,500 people who died when Titanic sank would have been joined by 710 more. The wireless saved 710 lives on the night of April 14, 1912. The public understanding of this fact, communicated in the press coverage that followed the disaster with an intensity that no peacetime event had previously generated, transformed public perception of wireless technology from a technical curiosity into a public safety necessity. Congress passed the Radio Act of 1912 within months of the disaster. The act required wireless equipment on all passenger vessels of a certain size, mandated 24-hour wireless watches, established the distress frequency and the procedures for distress communication, and created a regulatory framework for wireless communication that formalized what the Titanic disaster had made viscerally clear. The wire telegraph had no response to this. A wire did not reach into the North Atlantic. A wire could not have summoned the Carpathia. The specific limitation that had defined the telegraph since 1844, its dependence on physical infrastructure, was not a limitation that any amount of telegraph improvement could address.
The competition between wire and wireless telegraphy in the decade following Titanic was not the swift displacement of one technology by another. It was a slow, contested transition in which the established infrastructure of the telegraph industry, the commercial interests of its owners, and the regulatory framework that had been built around it created substantial resistance to the adoption of wireless technology, even in applications where wireless was obviously superior. Western Union in 1912 was one of the most powerful corporations in America. Its wire network covered the continental United States with a comprehensiveness that no wireless system could match. Its relationships with the press, with the financial industry, and with the federal government gave it political influence that shaped the regulatory environment for telecommunications. Its investment in wire infrastructure, the poles and the wires and the relay stations and the urban offices, represented capital commitments that would be stranded by a transition to wireless. Western Union did not simply accept the technological disruption that wireless represented. It argued through its lobbyists and its press relationships and its technical experts that wireless was unreliable, subject to interference, dependent on atmospheric conditions, incapable of the confidentiality that commercial communications required. These arguments were not entirely without merit. Wireless telegraphy in 1912 was subject to interference from atmospheric noise and from other wireless transmitters. The confidentiality concern was real. A wireless signal could be received by anyone with a receiver within range, while a wire signal required physical access to the wire to intercept. But the arguments were deployed selectively, with a consistency that reflected commercial interest rather than technical assessment. Western Union's technical experts were not neutral evaluators of wireless technology's limitations. They were advocates for a position that served Western Union's commercial interests, and the limitations they emphasized were real, but were being addressed by the rapid technical development that characterized wireless technology in the 1910s and 1920s. The interference problem was being addressed by frequency selection and by improvements in receiver design that made it possible to tune to a specific transmitter and reject others. The confidentiality problem was being addressed by encryption techniques and by the practical security that came from the complexity of the wireless signal format. The technical development of wireless was faster than Western Union's lobbying could contain. By 1920, the superiority of wireless for ship communication was incontestable. By 1925, amateur wireless operators, the ham radio community that had grown from the technical enthusiasts of the early wireless era, demonstrated that reliable long-distance wireless communication was possible without commercial infrastructure. By 1930, the broadcast radio industry that had grown from Reginald Fessenden's first voice transmission in 1906 generated revenues that dwarfed the commercial telegraph business.
The technical development that made wireless communication reliable for commercial purposes was not the work of one inventor or one laboratory. It was the accumulated contribution of dozens of engineers and physicists working in parallel across multiple countries, each contribution building on the previous ones in the way that technology development typically proceeds. The most important technical contribution of the 19-teens was Lee de Forest's development of the triode vacuum tube, the audion, as he called it, which provided a means of amplifying weak electrical signals by controlling a large current with a small one. The triode was not de Forest's invention in the strict sense. The diode that John Ambrose Fleming had developed in 1904 was the predecessor, and de Forest's patent claims generated decades of litigation with Armstrong and others. But the practical amplifying vacuum tube that de Forest built and marketed in the 19-teens was transformative for wireless communication. Before the amplifying tube, wireless receivers could detect signals but could not amplify them. A signal received from a distant transmitter was inherently weak. Its strength fell off with the square of the distance, and the limit on communication range was set by the receiver's ability to detect very weak signals. The amplifying tube allowed weak received signals to be boosted to levels that could drive loudspeakers or recording devices, or critically for commercial telegraphy, the relays and printers that produced a permanent record of the received message. Edwin Armstrong, whose contributions appeared elsewhere in this channel's stories, developed the regenerative circuit in 1912 and the superheterodyne circuit in 1918, both of which dramatically improved wireless receiver sensitivity and selectivity. The superheterodyne allowed receivers to be tuned precisely to a specific transmitter frequency and to reject signals at other frequencies, addressing the interference problem that had been one of the wireless technology's primary commercial limitations. By the early 1920s, a wireless receiver built with these technologies could reliably receive transmissions from distances that wire telegraphy required physical infrastructure to bridge. The technical gap between wireless and wire had closed, and in several important dimensions, wireless had become superior. The human element of the transition, the telegraph operators whose careers and identities were built on the manual Morse code skills that wireless was displacing, is the least documented and most important part of the story. The telegraph operator of 1900 was a skilled professional who occupied a specific place in the social and economic fabric of American life. The skill of sending and receiving Morse code at 20 to 30 words per minute, which was the professional speed standard, required years of practice and produced a fluency that was both a practical capability and a form of identity. Experienced operators described the experience of high-speed code work as a kind of flow state, the conscious mind not tracking the individual letters but processing the meaning directly, the way a fluent reader processes words rather than letters. This skill was not easily replaced by technology. The first wireless systems required operators trained in Morse code because the technology transmitted the same dot and dash signals that wire telegraphy used, only through the air rather than through a wire. The wireless operator on a ship was doing the same cognitive work as the wire telegrapher in a railroad office, listening to rhythmic electrical signals and converting them to language, with the difference that the signals came through headphones rather than a sounding instrument, and that the transmitter was a spark gap or a continuous wave oscillator rather than a telegraph key connected to a wire. The telegraph operators who learned wireless in the 19-teens and 1920s found that their Morse code skills transferred directly. Walter Weimer, who would send the last commercial Morse code transmission in 1999, had learned his trade in this tradition, the tradition of operators who moved between wire and wireless depending on where the work was, whose primary skill was Morse code regardless of the transmission medium. What displaced this tradition was not wireless itself, but the combination of wireless with voice transmission, the development of amplitude modulation that allowed a wireless transmitter to carry a voice signal rather than a coded signal. Fessenden had demonstrated voice transmission in 1906. By the early 1920s, voice broadcasting was commercially established. By the 1930s, radio telephone, voice communication by radio, was beginning to supplement and then replace radio telegraphy for ship-to-shore communication. Voice transmission did not require Morse code skills. A ship's officer who needed to communicate with a shore station could speak into a microphone rather than learning to tap a key. The specialized human skill that had been the essential element of both wire and wireless telegraphy was no longer essential.
The transition from telegraphy to voice radio was not instantaneous in any domain. Different applications transitioned at different rates, driven by the specific trade-offs between the two modes. Military communication retained Morse code far longer than commercial communication because military circumstances created specific advantages for coded transmission. A skilled operator could transmit coded messages more rapidly than voice in many tactical situations. Coded transmission used less bandwidth than voice, allowing more simultaneous transmissions in a crowded frequency environment. And the inherent secrecy of Morse code, which required a trained operator to decode rather than simply a receiver capable of capturing sound, had security value in military contexts, even in the absence of formal encryption. The United States Navy maintained mandatory Morse code proficiency for radio operators through the 1990s. The final International Maritime Morse Code Watch requirement was discontinued on February 1, 1999, 5 months before Walter Weimer sent the last commercial Western Union telegram. Amateur radio operators, the ham radio community, retained Morse code skills as a technical and cultural tradition long after commercial necessity had dissolved. The FCC required Morse code proficiency for amateur radio licenses with privileges on certain frequency bands through 2007, when the requirement was finally dropped. A substantial community of amateur operators continues to use Morse code voluntarily as a technical discipline and as a connection to the history of wireless communication. Aviation retained Morse code in a specific application, the identification signals transmitted by VOR navigation beacons, which broadcast their station identifier in Morse code on a continuous cycle, until the gradual retirement of those beacons in favor of GPS navigation. Pilots trained after the widespread adoption of GPS may have their first and only encounter with Morse code through the identification signals of navigation beacons they are transitioning away from.
The commercial telegraph's decline through the mid-20th century was a process of gradual marginalization rather than sudden displacement. Western Union, which had controlled commercial telegraphy in the United States for a century, diversified and adapted as its core business contracted. The wire network that had been the company's primary asset became a secondary asset as telephone lines provided more convenient voice communication and as wireless systems provided coverage in areas the wire did not reach. Western Union attempted to reposition itself as a financial services company, the money transfer business that would eventually become its primary operation as the telegram business declined. The telegram itself retained cultural significance long after it had ceased to be the primary means of long-distance textual communication. A telegram carried weight, the physical object, the delivery, the association with important news that a telephone call did not. Deaths were announced by telegram. War victories were announced by telegram. The culture of the telegram as a vehicle for important messages persisted because of the formality that the medium's physical form created, even as the practical superiority of the telephone for most communication was unquestioned. This cultural weight declined as the generation that had grown up with telegrams was replaced by generations that had grown up with telephones. By the 1980s, the telegram was an anachronism, a choice for formal occasions and nostalgic gestures rather than a practical communication tool. By the 1990s, the fax machine and then email had provided text communication alternatives that were faster and cheaper than telegrams, while retaining the written record that telephone calls did not. The last telegram was the end of a technology whose core function, rapid long-distance text communication, had been distributed among many successor technologies. Email carried the text, the telephone carried the immediacy, the fax carried the formality of a physical document. No single successor claimed the telegram's function completely because the telegram's function had been disaggregated among multiple technologies that each served part of it better than the telegram had served the whole.
The question of what was lost in the transition from Morse code telegraphy to radio voice communication is not a technical question. The technical answer is clear. Voice radio was more accessible, more flexible, and more capable than Morse code telegraphy for most practical applications. The question is cultural and cognitive. Morse code is a compressed symbolic system, a mapping of the letters and numbers of written language to patterns of short and long signals that can be transmitted rapidly by a trained operator. The compression is specific to the medium. A skilled operator at a key can transmit more information per unit time than a voice speaker can speak in circumstances where the clarity of the transmitted signal is marginal. At the limits of communication, low signal strength, high noise, interference, a skilled Morse code operator can extract messages from signals that are inaudible as voice. This capability is not merely historical. Emergency communicators and military operators who work at the margins of communication infrastructure continue to find Morse code useful specifically because of its efficiency at the edge of audibility. The International Morse Code Distress Signal, SOS, 3 dots, 3 dashes, 3 dots, is recognizable even in extremely degraded conditions, which is why it remains a recognized emergency signal in international maritime law, even though the communication infrastructure that generated it has been replaced. The cognitive skill that Morse code required and developed, the ability to hear rhythm as meaning, to process patterns faster than conscious analysis, is an unusual form of literacy that has no precise parallel in other communication systems. The operators who were most fluent in Morse code described the experience as similar to musical performance, a learned pattern recognition that operated below the level of conscious symbol-by-symbol decoding, producing meaning directly from pattern. This skill is nearly extinct as a professional capability. The amateur radio operators who maintain it do so for its own sake, as one maintains any technical skill whose practical necessity has dissolved, but whose intrinsic character makes it worth preserving.
Walter Weimer set down the key in Middletown, New Jersey on July 12, 1999, and the room was quiet in a way it had not been before. He had been sending and receiving Morse code for 47 years. In those 47 years, he had worked at coastal maritime stations and at the Western Union offices that processed commercial telegrams, and at various other facilities where Morse code was still the required medium. He had watched the gradual contraction of the domain where his skill was relevant, the maritime stations closing as radio telephone replaced radio telegraphy, the telegram volume declining as the telephone network expanded, the last applications of commercial Morse code becoming fewer and farther between. He understood that what he had done at Western Union on the morning of July 12th was not just the last commercial Morse code transmission. It was the end of the direct professional lineage from Samuel Morse's first transmission between Washington and Baltimore in 1844. The operators who had learned the code from operators who had learned it from the first generation of commercial telegraphers, the chain of skilled transmission that had carried through 155 years of American communication history, ended with Weimer's tap of the key. The technology that replaced it was not one technology, it was a succession of technologies, each better than the one before in specific dimensions, each capturing part of what the telegraph had done and doing it better, none capturing everything. Radio voice communication was more flexible, email was faster and left a record. The internet was all of these things and more. The satellite communication systems that linked ships to shore stations were more reliable and more capable than any wireless Morse code system had been. None of them required a human being to learn to hear rhythm as meaning. None of them could be operated at the margins of signal strength by a trained hand and a trained ear. None of them had the specific character of a technology that was, in its operation, a performance, a skilled human acting as the medium through which language traveled.
The Centennial Burb burns in Livermore, California. The Titanic's wireless distress signals were received by a ship 93 kilometers away. Walter Weimer's hand tapped the key for the last time in Middletown, New Jersey. These three facts are connected by the thread of technological displacement, the process by which the Centennial Burb burns in Livermore, California. The Titanic's wireless distress signals were received by a ship 93 kilometers away. Walter Weimer's hand tapped the key for the last time in Middletown, New Jersey. These three facts are connected by the thread of technological displacement, the process by which capabilities are developed, applied, superseded, and eventually preserved only in the memory of the people who used them and in the archives where the records of their use are kept. The telegraph did not fail. It succeeded so completely that the communication infrastructure it created, the expectation that distance could be overcome by technology, the commercial and regulatory frameworks that grew around long-distance communication, the professional communities of trained operators whose skills carried the system, became the foundation on which radio was built. Radio did not defeat the telegraph. Radio extended what the telegraph had begun, reaching the places the wire could not reach, surviving the disasters that the wire could not survive, eventually evolving into forms that carried voice and data and image in ways that Morse and Vail had not imagined when they tapped out the first message in 1844.